All right, thanks everybody. Thanks for sticking around till 5 o'clock. I really appreciate it. So my name's Nishant. I'm a third-year PhD student at the University of Michigan. My advisor is Jean-Baptiste Janon, and this is joint work with him, and then past work also with a couple other folks. So this is work in progress towards formalizing the active corner method in PVS. We'll talk about all of those keywords in just a bit. So in recent years, we've seen a proliferation of automation across a lot of different domains, right? Computing is getting cheaper to deploy, and we're seeing computers and chips in lots of places, including safety critical systems. I don't think at the end of the day, I need to talk anymore about why formal verification is nice for these things, but it is. But of course, it's hard. Joey talked about this. As it turns out, when you have the same advisor, you work on similar motivation for your work, and that verification is hard to deploy in these settings, right? The places where we write safety critical software are usually not the same places we can use verification, and that theorem provers are hard to use, hard to deploy scalably in industry. So this work focuses on automatic sort of push button verification to make it as easy as possible for users to do this collision avoidance verification in efficient and safe and provably safe ways. So past work by Jana and others has verified collision avoidance safety for ACAS-X, and that's really the inspiration of this work. So ACAS-X is an airborne collision avoidance system. Basically what it does is it'll issue advisories that come in the form of climb, descend, maintain altitude, etc. And it'll issue these advisories or commands to pilots in order to avoid mid-air collisions with, say, approaching aircraft in air traffic control settings. So, right, it's a safety critical system, and especially in the aircraft domain, aerospace uses a lot of formal verification already. And so there's been significant interest in verifying the safety of these advisories. How do we make sure that this control system is going to issue correct advisories given a configuration of, say, approaching aircraft and their dynamics? And so to abstract that, we're basically looking at a generalized collision avoidance task like this. So I want to outline what I'll be talking about. About the first half of my talk, in order to provide an introduction to this work, covers material from a paper I presented at FMCAD. So that's a statement sort of this general collision avoidance problem, an introduction to the active corner method, and our original sort of more geometric proof approach. And then I'll go into the second half of the talk, which is the work for our FTSCS submission. That's an outline to what we're doing with proof certificates, a different proof approach that's more algebraic and easier to formalize in a theorem prover, and what we've done so far to formalize this in PVS. I will note also this is again a work in progress talk, so there's a lot more work to do. Cool. So to generalize this sort of collision avoidance problem statement, what we're looking at here are two inputs. One, a convex polygon that moves along to a known piecewise planar trajectory. It might look something like this. And what we want to do is generate a safe region. Sort of this region in green, right, is the set of all places where if we have an obstacle here, a collision won't occur, right? It's outside sort of the reachable set as this object moves along its path. We want this region to be symbolic, so we can modify parameters, say at runtime, or solve sort of a more general instance of this problem and substitute in variables. We want it to be provably correct, because obviously, and we want it to be quantifier free. I'll talk about that shortly. So the key insight behind this work is that in order to construct these safe regions, we need to consider the trajectories of corners, but we also need to go a little bit further than just following corners. So in the past, proofs of this sort of advisory or trajectory safety has used two different representations of the safe region. The first of these is an implicit safe region, which follows sort of an intuitive definition of what a collision avoidance property might look like, which is to say along a path, an obstacle at some coordinates is a safe distance away, right? For all points in some set, maybe a trajectory set, you're far enough away in the x-axis and far enough away in the y-axis, right? So this encodes like a rectangle. You could say also you're outside of a polygon centered at xt and yt. Now, there's an equivalent representation, and that's an explicit safe region. And what that does is directly encode a region in space where you're never going to be as you move, right? That might be some equations, actually like some inequalities or paths in the plane itself, and these don't have quantifiers, right? This is just a direct Boolean representation. Now, there's benefits and drawbacks to each of these representations, right? Implicit regions are easy to prove safe. They're natively and sort of intuitively encoding a global property of collision avoidance. For all points, don't run into anything. But it's hard to use this at runtime because of the quantifier out front. If you're actually handed some instantiation of this problem, coordinates like width, height, coordinates for the obstacle itself. If I hand you 12,17, and then you go plug it in to some set, maybe a function for these trajectories, you have this for all out front, and you need to deal with it. Now, quantifier elimination is a natural choice to do this, but even CAD, right, one of the most performant solutions for quantifier elimination, is doubly exponential in the total number of variables, not just quantified variables, but all of them. And so in symbolic settings like the ones we care about here, CAD just doesn't hold up. It'll take too long to run, and not just like too long to run in an online setting where you need answers fast. You could let this run for like weeks on a computer, and because of the computational complexity, you may never get an answer back. So we need to do something different than quantifier elimination. So explicit formulations, because they don't have these quantifiers, are much more efficient to check safety, right? You just plug in your obstacle coordinates, you plug in some sort of symbolic constants, and you get either a Boolean answer or maybe some Boolean formula in a couple symbolic variables. But actually generating these explicit formulas is a huge pain, because it's really case by case, really specific to what are the trajectories that you're looking at. Are they parabolas? What kind of objects are you looking at? How are these polygons shaped? And it takes a lot of time, especially to prove this equivalence between your two representations in a theorem prover. This is like weeks or months of grad student time at a whiteboard. So past work that's used these two formulations has had some sort of repeated structure in how you go between, and if you do manually generate these explicit formulations, what you do with them. And the focus of this work is to bridge the gap automatically and back it up with proof certificates. So to step back, we're looking at a convex polygon that moves along a known piecewise trajectory. It might be, in this specific example, descending motion and then upward motion. We want to take this implicit quantified formula, and then we want to automatically construct a quantifier-free and geometric representation of this unsafe region, or you just negate this Boolean formula and you get the safe region. It might look something like this. This is sort of the full expression of what the safe region is. You've got one sort of set of inequalities representing this downwards motion. You got another set of inequalities representing this upwards motion, right? And you put these together and you get a representation of either the safe or unsafe region by negating the things you want. So the key idea here is to follow the corners. When we looked into this, we found that the boundaries of the safe region are going to come from two things. One, they're sides of the polygon, and a few key instances, like right up here and right down there, we use the sides of the polygon to construct this safe region. The rest of the time, it comes from the trajectories of its corners as it sweeps out this path. Now, which corners do you follow? This is where active corners come in. We pick active corners. We pick the corners to follow based on the angle of the trajectory. And we pick corners that represent the outermost extent of this polygon as it moves along this path. So if your motion is directed up and to the right, you're going to pick this bottom right and top left vertex because they represent the outermost extent of your polygon as you move. You follow those, and you, because it's translating, you can just shift basically the coordinates and get a function that expresses the motion of each of these corners. This works also for, not just rectangles. You can do this for, say, hexagon as well. Again, you're going to pick V1 and V4 such that they represent the outermost extent of this polygon as it moves. This is where convexity is important. If you have a non-convex polygon, then there's no real guarantee that your points are really necessarily defining the outside. You also don't get the uniqueness of angles sort of as you go around. So it's not just enough to follow the corners, right? You need to do a little more. And at transition points, these are places where the active corner changes, and we need to include the polygon when we construct this region. So if you just followed this black lower left parabola, the path of this one active corner, and then when you switch active corners, you follow now this bottom right, you miss what we call the notch at the very bottom. You would yield sort of an underestimate of the reachable set, and of course that kind of underestimate is really bad for safety. So you need to go further, and you need to include the shape of the polygon in constructing the safe region. So our FMCAD paper has one sort of attempt at proving the equivalence of our output, these quantifier-free explicit formulations, to an input implicit safe region. So we have a proof of equivalence, of course, that goes both directions, but for now I'm going to focus on soundness or the correctness direction, which is to say that if we tell you something is safe using the active corner method, this explicit formulation, it better be safe using sort of the more intuitive implicit representation. Recall that the explicit representation lacks quantifiers, it's just this Boolean formula, and the implicit representation has a for all out front. So we prove the contrapositive in our paper. We say that something that's unsafe in the implicit formulation implies that it's unsafe using the explicit formulation. And intuitively, what that means is that any point along any polygon somewhere along this path is going to lie either between the active corners, between this blue and this orange line, or it's going to lie in a transition point, either sort of at the beginning or the end of a segment of the trajectory. So we look at rotated segments of the trajectory. We sort of go piece by piece, and we look at places where there's no change in the active corner, which is to say you're following the same corner the whole time. And then you can sort of like look at another segment of the trajectory and follow a different set of corners. And what I want to convince you of is that in building our proof, we've directly handled the way that our algorithm accounts for the notch, right? Most of the time you're following the active corners, but at a few key places, you build in the shape of the polygon. And the proof really orients itself around that to start and end at places where we account for the notch. So the way that this proof works in our original FMCAD paper is that we bound the interior coordinates for some polygon somewhere along the trajectory, right? Some point xc sort of in between the beginning and the end. I don't know why I lost that line. That's weird. And it leverages some sort of geometric intuition that's hard to plug into a theorem prover, right? We reason about some interior point. It's at some sort of coordinate offset, but still inside of a polygon. And then we say, oh, yeah, this point lies on the center line of a different polygon that's shifted just a little bit. And because it lies on the center of some other polygon, we know that it's going to lie then in between these two active corner trajectories because they're made up exactly by following this corner and this corner as you move along. But this is hard to plug into a theorem prover, right? How do you formalize a geometric proof? This is something that's really challenging. And I can convince my lab colleagues, I can convince my advisor by showing them some pictures, and you can do a little bit of some hand waviness with proof by pictures. Reviewers will even accept a paper if you show them nice pictures, right? But theorem provers, they don't. Computer vision is good. It's not that good yet. And so you need to do something different to formalize this sort of geometric intuition in a theorem prover. And so that's why we looked at a different approach for our proof, and we looked at proof certificates in particular. So there's two different ways of that, in my mind, is sort of how we might formalize this. The first of this is sort of a formal proof of the correctness of our algorithm. That could be sort of an end-to-end re-implementation of what our original sort of geometric proof looked like. Better yet, it would be an end-to-end re-implementation of the whole active corner method, the whole algorithm that we have for generating these explicit formulas. If you could port that into an interactive theorem prover, you could get formally verified results, right? And that would be awesome. But it's pretty hard. So I will note that our implementation, it uses Python, and specifically we use SymPy, which is a symbolic math library, to do a lot of this sort of computation, in particular, identifying those transition points where the active corners change, right? And so we call out to an external library to do that. That is sort of like a point of weakness in the original method because it's could be sort of an arbitrarily difficult step where we're relying on some other library. But that's the sort of thing where it's really hard to get that encoded in a theorem prover. So instead, what we do is we want to show correctness for our results using certificates. And this is nice because, like I said, we've got this implementation. We've got this implementation in Python. It's unverified. And I think we did a pretty good job, but there, of course, could still be bugs. And especially when your output is some sort of complicated Boolean formulation, it might be numeric, it might be symbolic. It's hard to look at this and be like, oh yeah, like this 9 actually should be a 7, and it's coming from somewhere, right? And so in order to trust this implementation, what we envision generating are proof certificates so that a user can check whether or not these results are actually correct, right? So in addition to getting some output explicit formulation, you're also going to get an independent machine-checkable sort of reproduction of the proof steps, and it lets you as a user verify that you are indeed getting a correct answer. So this is like tools like CVC5 do this. You can get a proof, and it allows you sort of to verify things the way that like you get a counterexample out of model checkers or something like that. So we use the PVS theorem prover, the prototype verification system. This is PVS consists of two things. One, a specification language that lets you express formal models. It also includes a highly automated interactive theorem prover that lets you verify the correctness of these models. I should have a citation down below. It's a lot of great work by folks at SRI and NASA Langley Formal Methods, Natarajan Shankar, among a lot of other folks. So like I said, this geometric proof that we have in our FMCAD paper doesn't quite work when you plug it into PVS. It's harder to express these things. So we have a different approach in our FTSCS paper, that's easier to represent and prove properties about in PVS. And what we do, instead of representing the polygon as some sort of geometric object, which we reason about on paper, we talk about a polygon as a set of intersecting inequalities in the plane, and we manipulate them to yield an explicit formulation. So we basically generate algebraically subclauses from the explicit formulation based on which corners are active. I'll show you a picture in a second. And this is work in progress. At the moment, we handle straight line trajectories. That's not as much of a limitation as it might sound like. Because we look at places where the active corners don't change, we have bounds on the derivative of your trajectory function. You can sort of like bound this almost like, it's not actually Lipschitzness, but the way that you get sort of this cone for the bounds of a function. And I think that the logic we have for reasoning about linear trajectories, we can apply to the sort of like minimum and maximum bounds for the derivative of some trajectory function over a range. So what we do, right, for motion that's, say, directed up and to the right, we reason about a set of inequalities that represent the edges of this polygon, and we algebraically manipulate, say, the clause that represents this vertical left side and this top side, and we combine those to get this inequality here that represents this corner. And so we have sort of this like pairing between the algebraic steps and the actual geometric objects they represent. If you want to reason about the active corner trajectory in this property, you're going to use the equations that sort of represent the edges adjacent to it. Similarly, if we have motion directed downwards now, you're going to look at a different pairing of edges that represent, say, the edges that are adjacent to this active corner and that active corner for motion that's directed down to the right. We have this in our paper for diamonds as well as squares. More recently, we've gotten results for a hexagon, and we're working on some asymmetric polygons as well to generalize this approach. So our PVS proofs, they basically are reproducing the algebra that's in our paper, in our proofs. So this is an example of one of the lemmas that we've proven. This is sort of that soundness direction for a square. Like I said, we want to basically represent the polygon as inequalities in the plane, and we want to prove that you can indeed get this output explicit formulation from it. What we do basically is isolate x in these inequalities, right? There's x's here, there's no x's there, just yos and xos. You isolate these algebraically, and then you put basically two of these inequalities together, and you're going to get some bound on the sign. You put these two together, you might get that something is positive. You put those two on the right together, you might get that something is negative. And then you multiply those together to get one part of your PVS consequent. And then you do it for a different pairing of active corners to sort of finish off this whole implication and convince PVS that you have indeed done the right steps, and you get a nice QED at the end. So we have this lemma as well for the soundness lemma again for a diamond. This looks a little different, but we ultimately perform the same steps. And this is why we have sort of some confidence that we can generate these certificates. I envision, so at the moment we have sort of like a recipe, right? It's not exactly like the granularity that you need for an algorithm to generate these certificates, but you've got an idea of what you do with inequalities. You have an idea of which equations you use corresponding to sort of like what geometry, right? You pick equations that represent adjacent edges, you reason about corners, and you can produce these terms by performing algebraic manipulations like these. And when we've done this now for a square, for a diamond, for a hexagon in PVS, and we're playing with some sort of asymmetric polygons as well on paper for now, you follow the same steps. And so I have a pretty good amount of confidence that this will generalize to an asymmetric polygon. The actual implementing an algorithm to like automatically come up with PVS steps requires sort of being able to interpret what these inequalities are in a way that is, sort of challenging right now. And that's sort of the next step for this research. So yeah, in summary, I've presented an automated way of generating these symbolic geometric safe regions. They don't have quantifiers, which makes them efficient to use at runtime or at scale. And we can do this given a convex polygon and a piecewise trajectory it translates upon. I've talked about a couple different ways of proving correctness or soundness for the active corner method. The original sort of more geometric approach, and it looks at these bounds on the trajectory derivative that come from the polygon. We go segment by segment. I've also talked about our more easily formalized algebraic approach that uses inequalities to represent the polygon, and talked about some of the PVS lemmas and our proof approach. So we want to, of course, generalize this proof approach. I kind of sketched out how we have this recipe for the PVS steps, and we're working on sort of formalizing that algorithm in order to yield these certificates directly. I talked about how we want to be able to bound general trajectory functions that like some piecewise function f of x that, and we envision doing this by basically bounding the derivative of some sort of worst case minimum and lower and upper bounds. On the theory side, we're thinking about extending this method to rotating objects to handle, say, vehicle-type collision avoidance. Of course, cars rotate, and you can't do that much to model vehicles without them rotating. And to sort of push the theory also into higher dimensions. So instead of active corners in higher dimensions, say, look at maybe it's active the face of some polyhedron or an edge. That's sort of unclear, and the dimensionality gets pretty complicated. But if we can figure that out, then you have a really powerful tool for reachability, not just in sort of like the plane, but also in general parameter space, which could be really powerful. So I want to close by thanking you for your time. Thanks for a great workshop and for sort of having us all here. I want to acknowledge support and a lot of help from my advisor, Jean-Baptiste, Eleanor, another member of our group, also some folks at NASA Langley, Aaron Duddle and Tanner Slagle, who helped with the PVS and some of these proofs. And that funding for this work was provided by the Toyota Research Institute as well as a NASA fellowship. So thank you.
So, thanks. It was really very nicely illustrated how the proofs look like. So if you go back to the future work slide, so the long term, is this going to be a really complex proof that is then written out, or is this going to be a method to generate a proof that is specific to one trajectory? For example, for the rotation, that the proof will be written in a way that we generate different substeps, maybe the rotation phase and the straight phase? Or...
So rotation we don't handle right now, and it's complicated for several reasons. As far as what like a certificate structure might look like, we still do envision going piece by piece throughout sort of the trajectory, and you go segment by segment. Now, the reason that that's okay is that if we've generated an explicit formulation, first you have to identify all of those transition points. So we know what the active corners are in each of those regions once we've given you an answer, basically. And then we can construct sort of the cases for the proof, each of those segments, because we've identified them already. And so you might get sort of, many of those segments, and you basically get a proof case. Let's see. Sorry. This is the problem with having builds in your slide. Okay, so right, you would have like a segment that looks something like this, and then when the active corners change, it might correspond to motion that then like starts going up like this, and you're going to follow a different set of corners. You might follow these corners, and you could imagine sort of like another instance of this proof over this segment, but it's a segment that goes somewhere in a different direction. And so you would get sort of like a proof of like this implication for this, and then by following a different set of active corners, you might get sort of another proof case that holds over another range.
Okay, thanks.
Yeah.
Yeah. So what was your experience working with PVS? Did you find that it had a lot of support for these inequalities over real numbers, or did you have to like bake this in yourself?
It has, I think it supports that stuff pretty well. I'm by no means a PVS expert. Yeah, I think it's pretty supportive of this stuff. I think one of the challenging parts is that it can be hard to convince PVS of like relatively straightforward algebraic steps. And so like one of the things that we have to do is like there's a move terms command in PVS where you actually move like you say like I want to move the second thing on the right hand side of this expression to the other side, right? And I can see how like sort of for I don't know soundness or decidability or whatever reasons you can't just say like right. So one thing we want to do is isolate x. And like, if you could tell PVS just like solve for whatever, and have it be a thing that doesn't always work, but you know you can like quit out of the command if it doesn't. That's the kind of thing that would be really nice. But you have to do sort of more of that manual manipulation.
So like a lemma to say, in this case, solve for x.
Yeah, something like that could be pretty cool. Now the choice of PVS was mostly because we were working with these folks at NASA and they're experts in it. I think we could have built this in other platforms. Sam, obviously, you know Mohit, and like Mohit is an expert in Coq and stuff. So we worked on some of that, and then just sort of for convenience reasons, we decided to go with PVS. But I imagine you could do this in other platforms, and to be honest, I guess there's no guarantee that like necessarily PVS is definitely the way and definitely the long-term solution. It might turn out that some of the sort of like arithmetic that we want to do is like really hard in some places and really easy in others.
Well, I can tell you from my experience, it's not any easier to copy.
Yeah, well, that was the sense I got after a little bit playing with it too. Cool. Anybody else?
All right, so I have some question. So I guess that could be potentially very useful for verification of hybrid system
Mhm.
if the time can be incorporated to the
To the dynamics. Yeah.
It seems that it's currently time insensitive, right?
Yes.
So
Yes,
is
that
it
is true.
possible to incorporate some time as actual at this area?
So yeah, so we looked at a bunch of different ways of sort of like specifying these dynamics. And so initially we looked at like in the control community, right, and a lot of your dynamics get specified as differential equations, right? And so you could imagine, differential equations are quite hard. Obviously, there's lots of different subfields about like what to do with PDEs and how do you do approximations and all this kind of stuff. But even if you had like a parametric trajectory, right, x and y as a function of time defining sort of your trajectory. Now the trouble is that we do so in order to generate sort of like a quantifier-free mathematical representation, we express the path of this active corner trajectory and this active corner trajectory as functions in the plane. And so if each of these were encoded by something that were like parametric, then the trouble is that you don't actually know, like if you have a point that's here, this notion of being in between here and here is really hard to figure out because you have to go solve then for t, right? And like you could imagine that at the same t, you're here and there, but you've got a point that's like in between them somewhere. So how do you identify the t such that you know you're in between? So that was the trouble that we had looking at sort of parametric trajectories. We tried also functions that look like f of x, y equals like 0, sort of like level sets of 3D surfaces, kind of. That notion of in-betweenness mostly works for those, but you can construct pathological cases that get you into a lot of trouble. So we ended up going with sort of one variable but piecewise functions. Now I think, so yeah, it would be really great to handle sort of more complicated dynamics, but I think the underlying math, this notion of like in-betweenness that we really rely on gets super challenging. Yeah.
Yeah, just a remark. There is some work by Goodwell today that uses probabilistic models, time models.
Okay.
And in fact, they used it in an industrial context for drones for shows.
Yeah.
Yeah. For fleets of drones, and so as to control them to avoid collisions during a show.
Okay.
So maybe you could be interested in that, and that answers part of your question.
Okay.
But in general, they have a scheme that is like yours, but there is some security area around it, so they can move in something that is a bit bigger than the trajectory.
Okay. Oh, interesting.
All right, so thanks again.
Thank you.